So thank you very much. It's indeed an honor to give this lecture. And I think I'm returning back to Waterloo after about a decade. I think Carolyn had hosted me in the last time. So Sushanta, thank you for the invitation, and Dennis for all the arrangements. So yeah, I look forward to sharing some of our work with you. So basically, I'll talk about much of the time I'll spend on these atomically thin membranes we have been working on. And then I'll also talk about some other concepts in filtration and separations. So just to set the stage, we all know that water scarcity is a global issue. And this is being exacerbated by climate change. And it affects many of the countries of the world, some to a greater extent and some to a lesser extent. And water availability is one issue, but water quality is also another issue. So with water, it's often said like there is either too little, too much, or too dirty, right? So and so in terms of quality, we have to worry about a lot of different potential contaminants. So these may be salts. So if water is scarce, maybe there is seawater is plenty, but then it has salt, you have to remove the salt. So then quality becomes an issue, and then that can unlock more water sources. And so we have a lot of salt and ionic contaminants. We have small molecule contaminants. These days, there is increasing regulation on the perfluorinated alkyl substances of PFAS. Then there's pharmaceuticals, pesticides, and all of these things, and their degradation products that can make their way into water. There's, of course, bugs that can cause sickness, and then there could be particulates, microplastics, and so on. So there's a lot of issues in the water space. So if we want to use water and make it potable for or agriculture or other uses, we may have to remove some or many of these contaminants. Then if we look at other kinds of separation, so if we look at industry, and if we think about what we are going to need to move towards a sustainable civilization, separations actually plays a very major role. And if you look at US industrial energy consumption, about half of it is for separations. So it's really a very big footprint. And so clearly, if we want to move towards sustainability, if we can improve separations, that's one major lever. Then we also, as we think about moving towards sustainability, if we are thinking about electrification, then we need a lot of minerals, as you're aware. So we need like lithium for batteries, we need graphite for batteries, cobalt, nickel, rare earths. And these are projections of how many times of the 2020 demand we are going to need if the world meets the Paris Accord, and this is by 2040. So you can see that lithium will need 42 times more than 2020 demand. And this photograph is from Redwood Materials, which is a battery recycling company, and you can see these bags and bags of used batteries waiting to be recycled. So we need to think about circularity and how we are going to make efficient use of minerals. Otherwise, we can't just keep consuming at these levels and then throwing them to waste. And that means, again, we need to think about more efficient separations. So both in water as well as chemicals, minerals, separations become very important. And so we need separations to enable efficiency, electrification, circularity of materials. Also, material security and geopolitics plays a role in this. And then we also want to reduce costs, and we want to make sure we have minimal environmental impact, as small as possible. And membranes are very interesting in this regard. So of course, there's many types of separations, but membranes are particularly attractive because they often provide high efficiency separations. Many of the membrane processes are electrified, so the input is electricity, though you can also run them by thermal means. Then they're often modular, so you can scale them down or up. Many systems of separations, you can't really operate them at small and distributed scales very well, but membranes you can, so they can be modular and scalable. And often the membrane separation processes are less complex than other kinds of separations. So this is an article that appeared in Nature in 2016. So kind of a perspective article, and the authors are basically showing the US energy consumption. This is industrial, about half of it is separation. And their claim is if you replace distillation, drying, evaporation, these kinds of thermally intensive processes by membrane-based processes, you could reduce up to 90% of the energy input. Of course, not all energy is equal. So if you're putting in, kilojoule as electricity, it's not the same as a kilojoule of heat. So just keeping that in mind. But there is room for substantial savings. And if we look at water, this transition from thermal to membrane-based processes has already happened. And if you look at this picture here, these are pressure vessels, and inside that you have membranes that are wrapped. And these are used to desalinate water. So you apply pressure, water goes through, salt remains behind. And this, if you look at the capacity of desalination across the years, so this is 98 to 1000, and all the way this goes up to about 2020. You can see that reverse osmosis, the membrane-based process, the desalination capacity has gone up. Whereas if you look at these other two, which are thermal-based processes, so evaporation, condensation-based processes, they haven't really gone up much. And that's because of really major advances in membrane technology that made reverse osmosis more economical, more energy efficient. But there are still challenges with membrane separations. One is there is chemical and thermal stability issues. So in many cases, industrial separations, you can't operate membranes because they can't withstand the conditions. There's selectivity and permeance. So selectivity is to what extent does the membrane let what you want to pass through go through and retain what it doesn't. And permeance is how much resistance does it offer to the flow. So there's a trade-off, and membranes tend to get fouled. So you can get various coatings that form that then compromise the performance. And so if we can advance membrane technologies to tackle some of these issues, then there is opportunity to unlock more industrial efficiency. So this is just setting the context for some of the work I'm going to share with you today. So this is an example of some of the challenges, and I'm taking reverse osmosis as a case study. If you think about how much area of the membrane is used, it's about 1 kilometer square for some of the larger plants, so really large scale. Then there is room to further improve energy efficiency and how much water you recover versus how much you discard as brine. Then they're prone to fouling, as I mentioned, and this is a membrane after use. So this is a spiral wound membrane. So there's membranes wound in sheets, and you can see the fouling that happens. And it turns out that because of low chemical resistance of the membranes, you can't use aggressive fouling control, then you get these kinds of issues. Then this is basically different kinds of chemical compounds that were found in California waters. And so you can see this pharma, personal care products, antibiotics, industrial chemicals. And so if we want to recycle water and purify water, we need to make sure we are removing these. And many of these solutes cannot be effectively removed with reverse osmosis membranes. So that presents a challenge for recycling. And if you want to go to high pressure to account for very high osmotic pressure feeds, then many of these membranes cannot operate. So this is an example of specific challenges specific to reverse osmosis. So if we think about materials, by controlling the material structure and chemistry, we can have opportunities to further advance on membrane technologies. So the reverse osmosis membranes often have this very, very thin layer at the top, which is the selective layer. And the ability to make these membranes, which with a thin layer at the top, was transformational in reverse osmosis. Because then the rest of it is acting as a support, and the selective layer is a thin layer that doesn't offer that much resistance to flow. And then people have looked at incorporating materials like zeolites or metal organic frameworks into membranes. Then you can think about exploiting properties of materials like carbon nanotubes or graphene and graphene oxide. And all of these have room to advance some of the membrane technologies and address some of these issues. So today I'll talk about three different topics in this context. So first one is making membranes that are just one atom thick. So we make them out of graphene, and these can be useful for chemical separations as well as water purification. Then this other topic, which is actually one of the earliest research that we did in our lab at MIT, is using nanobubbles or air trapped inside small hydrophobic nanopores to do desalination. And then the last one I'll talk about is using naturally occurring membranes in wood, waste wood, basically, that can be used to remove pathogens and filter water. So I'll spend most of the time talking about this, and then towards the end, I'll touch upon these two topics. So why graphene? And I joined MIT around 2006-07, and that time graphene had just been isolated and it was gaining a lot of attention. And there was this new Center for Clean Water and Clean Energy that had started. And so we were thinking about, okay, what can we do that might be really transformative or offer membranes that are totally different with more stability, lower resistance to flow, and so on. And graphene with pores that selectively allow molecules to pass through seem to be a very, very promising material. And so the core idea is these well-defined pores in this atomically thin layer, they enable rapid site selective transport. Because it's thin, they offer very less resistance to flow. So you can think about making more efficient, more compact systems. Mechanically, it's very strong, so you can actually apply very high pressure. The pores are rigid compared to many of the membranes. So what that means is if a molecule is bigger than the pore, it's not going to go through. The barrier is going to be extremely high. And that means if you have a wide variety of contaminants, as long as the pores are smaller than the contaminants of interest, it will just reject all of them. You don't have to worry too much about the chemical interactions. Then these are very chemically resistant. So that means you can operate them under aggressive or harsh conditions, and you can do better cleaning and fouling control. These are designable in the sense that you can relate the pore structure and the underlying membrane structure to the transport properties. So they can be kind of predictable compared to more empirical designs for many of the membranes. And then finally, one can imagine making these on a roll-to-roll basis. So you can think about a pathway to scale up. So all of this seemed very interesting and promising. And so then we asked, okay, how can we realize this potential? So we looked at how can we control pores in graphene? How does transport happen? And there's very interesting interplay between the graphene structure and what it sits on. And then how do we make membranes that are robust, that actually work? We don't want to make 10 membranes and 2 of them work, 8 of them don't work. If this has to be practical, all of them have to work. So how do we make them robust? So these are some of the key questions that we had in mind as we went through. So graphene, there's been a lot of advances. You can synthesize it by chemical vapor deposition at scale. You can do role-based processing, and this has been done for various applications. So we can start with this CVD graphene, so chemical vapor deposition, and this is an established method. So you get a single layer on a copper foil, and people have made it at pretty large scales. So then you can put it on a porous support, and we chose these track-etched membranes. So they have these cylindrical through holes, and the support is very well defined. So we know what the graphene is doing rather than convoluting it with the support. So we picked this, and we can transfer graphene. So take graphene on copper, we just press it onto this polycarbonate track-etched membrane support, and then we remove the copper and we get this graphene composite membrane. So there's a layer of graphene on the polymeric support. And this is what it looks like. So you can actually see the graphene, and you can see it's covering these pores. So in 2008, there was a very seminal paper that was published by the McEwen group. So Scott Bunch was then the student doing this work. And what they did was they made these nano balloons out of graphene exfoliated from graphite. So now if the graphene is not permeable, then the gas trapped inside is not going to go anywhere. And so the balloon will stay as it is. But if there is permeability and the gases pass through the graphene, then the balloon, if the balloon is under high pressure, it's going to deflate over time. So by looking at the shape of this, they were able to deduce that graphene is practically impermeable to all gases at room temperature conditions. So now the question is, these are like nano balloons. I think these were like a few microns in scale, in diameter. If you were to scale it up to macro scale, so let's say centimeter scale, what happens? And we wouldn't expect graphene to be pristine. There might be some defects. And what happens if you have CVD graphene grown on copper? So we asked those questions, and in general, we might expect there's some areas where graphene is just gone or damaged, and then others, maybe there is some flow through it, or maybe there isn't. That was the question. And it turns out that if you look at pressure-driven flow, the scaling is very different. And so any holes that are less than about 50 nanometer in our experiment would block the pressure-driven flow. But if you look at diffusion, the scaling is different than pressure-driven flow, and it means that any hole bigger than about 3 nanometer would practically make the graphene transparent. So by comparing these two modes of transport on the same membrane in the same setup, we were basically able to probe, are there any pores in this few nanometer range in the graphene? And we did this experiment. I won't go into detail, but we have a membrane and two baths, and then we can look at pressure-driven flow and diffusion. And what we found is just the support, there is a certain rate of transport. You put the graphene, it drops by about 90% in pressure-driven, but in diffusion, it only drops by about 50% or so. So clearly, there's a discrepancy between the two, which means there is some pores that are in this few nanometer range. And indeed, we were able to go ahead and image these. So these images were not so easy to take, but at that time, but we indeed found that there were many pores in this few nanometer range, and were able to show that if you look at the flow of molecules by diffusion, so this is salt, some small molecules, and this is a polymer, which is bigger in size, this bigger molecule doesn't go through as quickly, even at the centimeter scale. So you can have a centimeter scale single layer of graphene, and it's partly blocking this bigger molecule. So we were quite excited by this result because we have a one atom thick layer, which is actually showing some selectivity. Of course, it's not very good here. And so that was good, but if we want to do molecular scale separations, where much of the energy intensive separations happen, then of course we have few nanometer holes that is going to kill our separation. So we have a problem as well. And I'll come to how we deal with this problem. So in parallel, we are looking at, okay, can we create pores at the molecular and ionic length scale? So we want to make pores that are in the sub-nanometer regime to about 1 nanometer, 2 nanometer regime. And we borrowed from previous literature. So there was literature as to what happens if you irradiate graphene with ions, and you can make these defects. And then there's this paper on unzipping carbon nanotubes. So there's a potassium permanganate-based etchant that only attacks defects. So we thought, okay, let's make these defects and then etch them chemically. And that worked. So we irradiate the graphene that makes defects, and we etch them out. So we can see that the pores, so this is the pore size distribution, 0 to 2 nanometer scale. And again, we do use high resolution microscopy to characterize it. And this data took about a year to do because it was quite painstaking, and we had to image large areas to get statistics. But you can see these pores start to emerge, and then you can basically see these pore size distributions coming up. And the number of pores, we can get about few times 10 to the 12 pores per centimeter squared. So you have multiple pores in a 10 by 10 nanometer area. So that was very promising. And these are some images. In the TEM, a lot of junk gets deposited on the graphene, and some is already on the membrane. And it's not yet fully understood what it does. So in papers, you might see these super clean images. But when we think about large scale systems, that's not really representative. And so there's a lot of this stuff. So you can see the lattice, mostly silicon and other stuff. and then you can see these pores marked by the red arrows. If we skip ion irradiation, then we don't get pores as we would expect. So now can we get selective transport at the ionic scale? And to do that, we again measure transport by diffusion. So we can look at different dyes and we can probe them using a spectrophotometer, or we can look at salt diffusion and we can look at membrane potential. So if you put salt of different concentration and measure the potential, then you can see the differences in transport between the two ions. And potassium and chloride, they have very similar diffusivities in water. So now if we measure a potential, it tells us there's some selectivity between these two ions. And then we can etch it to grow the pores further and repeat this. So after doing this experiment, what we found on the x-axis, we are etching. So we are basically creating more pores and making them a little bit larger. And we are comparing potassium chloride and this small molecule, Allura red. And you can see that potassium chloride goes up quicker and then it levels off at 1. So at this point, the graphene is essentially transparent. Everything is governed by the support. And then here you can see that the dye actually picks up later. So there is a window in which the membrane is able to distinguish between the potassium chloride and the dye. And again, this is single atom thick membranes at the centimeter scale. And then between potassium and chloride, at the few minutes each time, we can see a selectivity come up and then it goes down. So what this means is that the membrane is selective to potassium and then it's dropping off. Again, this is consistent with negatively charged functional groups and small pores, which would allow K plus to pass through. So that's the picture that emerges as the pores. This is etch time. As we make bigger and more pores, first potassium ions preferentially go through. Then you have salts going through, but not the dye, and then everything goes through. In this regime, the graphene is basically transparent to everything, all of the both salts and the dye molecule. And we can think about transport pathways that account for what is going on. So this was very interesting because now we have something which we can tune selectivity at the sub-nanometer scale with a 1 atom thick membrane at the centimeter scale lateral dimensions. So we, of course, have to deal with defects. And I talked about there were these nanoscale defects, and then you can also have larger defects. So how do we design membranes that actually are robust against these defects? So one concept is here. So let's suppose this dark circle represents a support pore, and these red dots represent defects that are not selective. So everything passes through. And then we create selective pores everywhere. Now, in this configuration, if you focus on this, we have flow through graphene. So all of this area of graphene, that's in parallel with flow through these leakages in series with support. If the graphene resistance is high, leakage dominates, nothing works. But if we isolate these leakage, so let's say the pores of the support are smaller, then what happens is you have this configuration and the leakage is in series with the support. Now you can pick a large enough support resistance that it blocks the leakage while allowing flow through the graphene. So because the defects are very small areal fraction, usually less than 1%, this strategy can work quite well, and we can model it and see that we can get good selectivity, and it's governed by these two dimensionless parameters. So one is how resistive are the selective pores compared to other defects, and what is the defect spacing compared to the support pore characteristic length scale. And that makes the membranes significantly more robust. And we have used this principle over and over again, and it's very effective so that we don't have to worry about a little defect here and it kills the membrane performance. So we first tried to look at apply this for gas transport. And depending on the differences diameter between the pore and the gas molecule, you can have different regimes. So this is what is the effective area that the gas molecule sees. If the pore is bigger than the gas molecule, then all the data points are here. So the pore appears to be a certain area. But if the pore is smaller than the gas molecule, the molecule has to squeeze through, and the flow rate basically effectively drops. So based on these, we can do a design of the support And I won't go through the details, but we use the same principle to identify which kinds of supports are going to be necessary in order to observe selectivity between gas molecules. And we did this experiment by taking graphene, putting it on this anodized alumina membrane, which has these straight pores. Then we create pores by ion irradiation and plasma. And what we see is as we increase the plasma each time, the flow rate through the membrane goes up and then it flattens out. And this is the support. So at some point, the graphene basically is not adding any resistance. But if we look at the ratio of these two gases, so helium to sulfur hexafluoride. So helium is about 3 angstroms, sulfur hexafluoride is about 5 to 6 angstroms. We can see that there is a selective transport that goes up and then it goes down. So as we make pores, we are making pores that are selectively allowing helium to pass through, and then they become non-selective as they grow bigger. So this principle works. Of course, the selectivity is not great in these membranes. And but at the same time, we are able to explain this nicely using the kinetic diameter of the gas molecules. So all of these gas molecules fall nicely on this black curve, and here it's normalized by the mass of the gas. So you can see the selectivity depending on the diameter of the gas molecules. And we can explain this based on the pore size distribution that we create. So it agrees. So we can take the pore size distribution and it explains the gas transport rates that we see in our membranes. So we still have some defects. Selectivity is not great. Can we somehow seal these defects? And remember, I mentioned that even gases cannot pass through graphene if it is pristine. So then what we thought of, if gases cannot pass through or molecules can't pass through graphene when it's pristine, where there is defects, now these molecules should be able to pass through if the defects are larger than the molecules. So can we then use that to localize chemical reactions only where there are defects? And if we can do that, then we can basically plug in the defects. So what we did was very basic polymerization reaction. This is not the best chemistry to use, but the first one that we picked. So we take these two monomers and they polymerize to form nylon where they meet. So if we add the monomers from opposite side of our support, this is fluorescently labeled in this case, they go and form polymer plugs in all the support pores. Now, if we put graphene on it, then what happens is that they will form plugs only in areas where there is defects. And then we also can put atomic layer deposition or other methods that will also selectively go to defects. They seal the defects, and you can see this going down further. So we can actually localize chemical reactions only at sites of defects using the impermeability of pristine graphene. And then if you look at salt leakage, this is just the support. If we add graphene, it goes down, but not by a lot. We add hafnia, it goes down, and then we plug in, it goes down a lot. So we can basically scalably block these defects using these kind of reaction localization only to the sites of defects. So with that, we are able to measure water flux as a function of osmotic pressure and do some dye rejection and salt rejection experiments. So here we got rejection of dye molecules and a little bit multivalent salts. And our experimental values were consistent with the molecular dynamic simulations at that time. But we still have this issue of when we make pores, there is this tail of the pore size distribution, and these are all leaky. So if you have a bulk three-dimensional material, then the transport is governed by the smallest pores, right? Because you have to go through a small pore to pass through. But if you have a two-dimensional material, transport is governed by the biggest pores because they're all in parallel. So this becomes a problem. So of course, the previous method that I talked about can also be used to address it, but are there other ways to do it as well? And if we can't tackle this tail, then we are never going to get good selectivity. So how do we do this? So what we thought was, what if we have a larger pores, if we have big molecules that are too big to pass through these pores, but they can interact across these pores, they should be able to lock across the graphene pore. right? So imagine like you have a wall and there's a hole in the wall, and then two people shake hands through that hole, they are locked in place. So that's the idea. And so we can introduce molecules on opposite sides simultaneously, and they should be assembling across the larger pores under certain conditions. So we did this with polyelectrolytes because they're just charged polymers. They will interact electrostatically very readily. And what we found was if you introduce oppositely charged polyelectrolytes at the same time, you can indeed block transport of the small dye and salt. And this doesn't happen if you do it serially. So you need both molecules oppositely charged to be present at the same time on the two sides of the membrane. And so with this, we can significantly push up salt rejection. This multivalent salt rejection is pretty much 100%. And then MD simulations also show if the pore is large, then it favors assembly of these molecules across the pore. So this is very interesting. And this allows us the ability to tune the selectivity of the membrane quite readily. So with this, we measured multiple ions in salt mixtures. And if you assemble polyelectrolytes, you can actually tune salt transport over 2 orders of magnitude quite readily. And then we also get some very interesting selectivity between rare earth ions. So this is somewhat difficult to obtain. And we don't quite fully understand what exactly are the mechanisms responsible. But there's an interplay of steric, like size-based effects, as well as interactions between these ions and the charges on the polyelectrolyte. So there's a very interesting and tunable system that we can change the functional groups and tune it for different ionic separations. And there is very interesting potential here to actually bypass very environmentally intensive processes for ion-ion separation, especially for rare earths. So switching gears a little bit, the other broad class of separations is organic separations, and they are important in pharma manufacture, petrochemicals, biofuels, and so on. And stability of the membrane, selectivity, and permeance, that is resistance to flow, all of these are challenges in this space. So here we put graphene on a polyimide trackage membrane support. So this is much more robust, and many of you might know Kapton films. So these are basically Kapton films with holes drilled through it. And we put graphene on top, and then we can make holes, and then we can see that we can selectively let through small molecular weight organics while rejecting the bigger molecular weight organics. And then we looked at, okay, if the membrane pores are rigid, they should actually allow transport based on the size or geometry of the molecule. And can we actually detect that? So here we plot versus viscosity, pure liquid permeance. So just one liquid at a time, we use pressure-driven flow. And if you look at this black line, this is just the support without graphene. And the permeance scales inversely with viscosity, as we would expect. And if we normalize the permeance by viscosity, the support is a flat line. But here we can see that these different molecules are all over the place. But if we plot it against the smallest cross-section of the molecule, then this curve suddenly collapses. So it goes from here to this nice curve. And what you can see is below about 0.5 nanometers, the molecules are going through quite readily. But if the cross-section, smallest cross-section of the molecule is above 0.5 nanometers, it doesn't go through. So again, it's consistent. We can make pores at that size, and molecules that are bigger in cross-section than that pore size are not able to pass through. And so we see that the flow rates actually explained by this smallest molecular cross-section, and here continuum flow breaks down, basically. Now you're looking at molecular size-based effects. So these membranes are extremely robust. So we operated them in like 9 different solvents, and this is like 400 hours of testing. And these red dots are methanol flow rates after going through all of these and coming back to methanol. You can see it's flat. And then in mixtures, so this is these molecules added into acetone, And this is before and after. And you can see that the linear alkane, that shows no rejection, but the cyclic and branched alkane, they basically show rejection. So again, it's consistent that this effect works even in the mixture. And these membranes have very, very low resistance to flow compared to other membranes that have selectivity at this kind of length scale. So it opens very interesting possibilities for efficient separations of different molecules. So one problem that one of our sponsors was interested in is this hydrogen or dehydrogenation reaction. So this is useful. There's many in petrochemical refining, but also hydrogen storage. And in this particular case, if you look at Decalin, so this is two cycloalkane rings, and then you dehydrogenate, so you get naphthalene and hydrogen, but the reaction doesn't go to completion. So what you have to do is take this out. You have to condense out the condensables and then reheat and inject it back, and you take out the hydrogen. So that's a very equipment intensive and energy intensive process. So they wanted a membrane that can operate under the reaction conditions and just bleed out the hydrogen. So that's the idea. So we have a separation here that operates at the reactor temperature, which is typically around 200 to 250 in this case. So these membranes did do the job, and you can see that they have decent selectivity versus these hydrocarbons. So these are the hydrocarbons we tested them with. And if you look at the hydrogen flow rate versus time, again, it's flat, 500 Kelvin over 5 weeks, no change. And this, there is some interesting trends between these, which we believe have to do with how these molecules are interacting with the graphene surface. And again, they have extremely low resistance to flow. So again, this is very promising for these kind of integrated reactors. We also observed some very interesting effects, like if we sweep the temperature, the selectivity between, say, hydrogen and methane in this case, as well as the flow rates, they kind of cycle. And hydrogen flow rates increase with temperature, but the activation energies were not quite consistent with anything we would expect. So we were scratching our heads for almost like 1 or 2 years doing all kinds of control experiments to rule out possibilities. And in the end, what we think is the most likely scenario is if you have functional groups on these pore edges, then as you change the temperature, these groups are vibrating. And so if you look at the apparent size of the pore, as these groups oscillate, the pore size fluctuates. And so you can see that at different temperatures, like this particular pore, you can see like larger openings happening because of the fluctuation of these molecules. And so effects like that seem to be quite responsible for this temperature dependence. We have also done work in scaling up these membranes or demonstrating you can do that. So this is work with John Hart and Piran Kedambi, where it's a roll-to-roll fabrication of the graphene, and then you can do casting of polymer and defect sealing and oxygen plasma. And we were able to show these membranes outperform conventional membranes in dialysis separations. So that was the majority of my talk. So maybe in the next 5 to 10 minutes, I'll talk a little bit about these two other topics, which are different, like interesting in their own aspect. So I talked about water desalination, and there is membrane-based processes and thermal. So thermal processes have high energy requirement, but they are good at rejecting all non-volatiles. And membranes, they have issues including fouling, scaling. They have poor resistance to chlorine, which used to be the major thing to use for biofouling control. And many emerging contaminants are not rejected, as I mentioned. So we thought, can we combine the best of these two? And the idea we wanted to pursue or came up with was, instead of this polymer as a selective medium, replace it with air while retaining the pressure-driven. So it looks like a reverse osmosis membrane, but instead of a polymer, you have just vapor, so nanobubbles of vapor. And then this whole process can be isothermal. So it involves evaporation condensation, but we bring those two together within a submicron gap. So there's no temperature issue. And so what happens is you decouple material properties from transport properties. That means you can pick materials with higher resistance to chlorine and improved biofouling control. You can get potentially higher flux and selectivity in this case, and you can get better rejection of emerging contaminants like boron and boron. And then you can do membrane design by controlling the pore geometry. So we did some basic modeling, and we are able to show that if you are at moderately elevated temperature, you should be able to get like very good fluxes. But as we are looking at the mechanism, there is different things going on. So there's evaporation of water molecules from the surface, scattering from the surface, and then when a water molecule hits the other meniscus, is there a condensation or is there a water molecule coming out? And this property is very important in a variety of transport phenomena, including in the atmosphere, in other systems, but it's very difficult to measure. So that was quantified by this coefficient, accommodation coefficient or condensation coefficient called sigma. So if sigma is 1, it means if a water molecule hits the meniscus, it's going to condense. If it's 0, it means it just reflects off every time. And of course, reality is somewhere in between. So that was an unknown. So we made this membrane. So how we did that, we took alumina membranes, which have these circular cylindrical pores. We impregnated it with photoresist. We etched, so we can etch out a known distance by controlling the time. And then we coat this with a hydrophobic material. So now you have a hydrophobic cylindrical pore of a control length. And the membrane looks hydrophobic on the top and hydrophilic on the bottom. So we are able to show that the membrane actually rejects salt as well as dyes. So you can see that it's 99.9% rejection in this case. And then the question is, if the pore becomes smaller and smaller, what dominates? Right? So let's suppose this is a long pore, then diffusion inside the pore is going to dominate. But there is these interface resistances that are associated with this water molecule condensing or reflecting off. So if you have a short pore, does the interface dominate? And if the interface does dominate, we are going to get lower fluxes than if it didn't dominate. So we did some very careful experiments. Again, this is much easier said than done. It took like 4 years to get this to work. So it was a lot of painstaking work. But if we look at the pore aspect ratio, so this is long pores and short pores, and these are different theoretical fits. You can see that at the long pore, it's fitting very nicely. But if we assume a 50-50 probability here, at the short pores, it systematically deviates. And we are able to show that from this, we can actually measure this condensation coefficient. And for a set value, basically, it collapses all of these data points. And we can obtain the condensation coefficient as a function of temperature. And the values we obtain are basically in this 20 to 40% range. So what it means is that if a water molecule hits a meniscus, most of the time it will reflect or it will cause another molecule to come off. So that was a very interesting basic measurement that we are able to do. And later on, this is my student Jong Ho who did this work. He collaborated with Anthony Straub at Boulder, and they have advanced this quite a bit. So we did forward osmosis. They were able to apply pressure and actually show, this was relatively recent, 23, that the membrane can reject boron. This is a small molecule emerging contaminant, urea, and everything very well. So if you take current polyamide RO membranes, then they can't reject urea and DMA boron very well. But these membranes were able to get very good rejection. And if you expose them to chlorine, which degrades these membranes, then this membrane is actually stable, whereas the state-of-the-art polyamide membrane rapidly loses its performance. So this was this took a very long time, right? So the original idea was in 2008, and this is 2023. So but it's still proceeding. So I'm hopeful that this will someday actually be practically useful. And then coming briefly to the last point, last aspect. So this is really motivated by the need for clean drinking water, and especially the burden of waterborne disease. And there is many challenges: awareness, affordability, access, and acceptance. These are some of the key challenges for clean drinking water when it comes to access, especially for people with low income. So this idea came out when I was at this conference. So that's me there. And it was a NATO-sponsored conference that brought together people from different communities. So there was engineers doing fluidics at the small scale. So I was in that category. There were people studying water flow and fluid flow in plants. So what happens when you have crops that are in drought or trees that are water stressed? And there were people studying water in the geophysical context, like ancient water trapped in rocks, or even there was a person studying what happens when bats pee on Angkor Wat temple and how it causes erosion and stuff like that. So quite an interesting mix of people. And we have seen what happens water transport in plants, right? So there's evaporation from the leaves, and you have water being drawn up, so sap flows up. And it turns out that the water pressure at the ground level is typically close to atmospheric, but at the top, it starts to drop, right? So when we swim, if you go down, the pressure increases, but now you start at atmospheric pressure and you go up, the pressure drops. So water is actually under tension. And if you have a tree, let's say a 90-meter tall redwood tree, the pressure can be negative, like many, many atmospheres negative. Now the tree has to pull it up and water is going to be in a metastable state. So you can have vapor bubbles forming, and if that happens, it's going to cause failure and the plant will die. So to tackle that, plants have this very interesting system. So this is in a pine branch, and you can see that these channels, so the tissue that does this job is called the xylem tissue. And if you look closely, there's these funny structures on the side, and there's these dome-like structures with holes in it. And then inside them, you have this spider web-like structure. So what is happening is that these spider web-like structures actually plug against this hole and block the flow if there is a bubble. So that's how plants basically prevent systemic dry out, because these tubes are short in length, interconnected through these features. And so if there is a bubble formation, it just blocks off. And it does that using very fine pores. And so this is happening in flowering plants, or it does it with these kind of flexible membranes, which happens in conifers and ginkgo. So if you look at the length scale now, that's 2 micron. Most bacteria in the micron scale, and protozoa and all in the few micron scale. So they should be able to filter these out. And if we can, these membranes already exist. So if we can make water filters, then they would be simple to make, eco-friendly. So these would be biodegradable. And in fact, you can use waste wood that's normally not used for structural or furniture purposes, but discarded or made into pulp. And it's very cost effective. Sometimes it has very low value as a byproduct of the timber industry. So we looked at what are suitable structures and found that the conifers and ginkgo actually have the right structure, and it's very straightforward to actually filter water through this. And you can see pigment is being captured in the first few millimeters corresponding to the length of these tubes. So whenever it has to cross through these membranes from one tube to the other, that's when filtration happens. And we are able to show that that's where bacteria, which are fluorescently labeled, get trapped. And we are able to get 99.99% rejection of E. coli in this particular experiment. So what we did then was, okay, people haven't looked at this as a material for water filtration from an engineering perspective. So what are the flow rates? If you dry it, we found that the permeability just drops down very dramatically. So quarter inch, you get quite a bit of permeability when it's dried, but it's still much lower than what happens if it's fresh. So when you dry it, permeability drops, and if it's thicker, you get no flow. So now, of course, that's an issue because you can't dry it, and we are able to trace this behavior to percolation networks inside the xylem tissue. And that led to very interesting engineering solutions. So for example, if if you take a quarter-inch long filter, then it has good flow, which is in blue, but not very good rejection. If you take half-inch, rejection marginally improves, flow drops dramatically, so it's useless. But if you take this half-inch filter, cut it into two, and stack it back, now you're connecting pathways at the cross section where you cut it. Now you get much better rejection than the quarter-inch and pretty good flow rate. So it's very counterintuitive, but because of the percolation networks, this kind of works. And we are also able to preserve this using just an ethanol soak, and you can get these in dry form, which you are able to show you can store for like 2 years and they still work. So we did experiments. This is in North India in collaboration with Himothan Society, which is an NGO. And we are able to take contaminated real spring water and show that the filters actually remove the contaminants, and also send these filters to a third-party lab in New Jersey. And they showed very good rejection, not only of the bacteria, but also of viruses responsible for most of the drinking water diarrheal diseases. So these provide pretty good protection against waterborne pathogens. And we have done a lot of user-based studies, some different designs. This is my student, Kritika, who led this project as her PhD. And she designed this and interacted a lot with people to learn about what their preferences were, what their concerns were, and so on. And we found a lot of broad spectrum, ranging from people who are blissfully unaware to those who actively sought better solutions. And I won't go into detail, but there were very interesting things like, if you can make low recurring costs, that's much better than larger costs few months down the line. That's a major barrier. And you can see there is a lot of different perspectives here. And there's a lot of engagement. So this was a high school student, Varsha, who worked on the project, and she got a prize at this Intel Science Square fair. And then Kritika was doing demos and engaging people at a museum in Bangalore. And we have this website which is designed more for like science experiments, and a lot of good feedback, including from a coach of school students, and saying that this project inspired the kids on how to research issues, understand that billions lack basic necessities, and they can put their brains together to address these issues. So it was really heartening to see the engagement in science that something like this brought about. And there is a lot of possibilities of making different devices, and the recurring cost of the replaceable actually is very low, with the cost per liter of water being quite comparable to conventional home water filtration. And we are trying to push this ahead through a startup. And one of the areas where I really feel passionate about is disaster response, where instead of shipping water, you could ship filters that are fully biodegradable, very agile, and can provide water right after disaster strikes. So with that, I'll conclude here that nanostructured materials can be used to engineer flows and used for separations and filtrations. We showed that it's possible to filter molecules across just one atom thick membranes. There's a novel osmosis membrane concept using vapor nanobubbles, and the xylem tissue in wood can be used to make drinking water filters from waste wood. And of course, none of this would be possible without all my fantastic group of students and postdocs and lab members. Actually, Sharafat, who is sitting here, was in the lab last year for several months. And then all our collaborators, funding, and facilities. And yeah, with that, thank you all for your attention.